welcome everyone to this UK SPS seminar today. If you are here, I guess you know what is UK SPS, so I don't need to say too much, right? Today, it's our pleasure to have Zhiyun Qian, Professor Zhiyun Qian from UC Riverside to give us a talk. Zhiyun is the Everett and the Imogen Ross Associate Professor in the CSE department at the University of California, Riverside. His main research interests are in the area of system and network security, including vulnerability discovery, side channel analysis, applied program analysis, system building, and measurement and analysis of the real-world security problems. He is the recipient of the ACM CCS Distinguished Paper Award in 2020, Applied Networking Research Prize from IRTF in 2019, NSF Career Award in 2017, Facebook Internet Defense Prize finalist in 2016, and the Most Creative Idea Award from GeekPong 2016. So today, his talk will be on weaponizing network side channels from TCP hijacking to DNS cache poisoning. I believe this is based on a series of high quality research published in NDSA's Usenix Security and CCS, including the one that won the Distinguished Paper Award in CCS last year. So I will say no more and pass the stage to Zhiyun, please.
Thanks for the introduction, Changyu. So let me get right into the talk. So before I get started on the side channel stuff, I just wanted to spend like 2 minutes on my research philosophy to sort of set the stage. So the way I look at security research is, and a lot of people define security research to be understanding how bad guys can take advantage of man-made rules. Basically, whenever we develop or design a set of rules that are complicated enough, we're almost always bound to introduce loopholes. So think about our tax laws, for example, full of loopholes. And even thinking about our video games, which are sort of a much simpler kind of system compared to what we have in our real world computing systems, they also can have loopholes. And here's one example of a video game which I used to play a lot, and it's called StarCraft. It's a real-time strategy game. It's a competitive game. A lot of people compete for their career, actually. So what they do is you can move your unit around the map. And in this case, we're trying to get past some enemy structures. And apparently they should be blocking off the terrain completely. However, if you try to build a structure yourself right next to the enemy structures, well, then it would actually cause the unit itself to enter some kind of floating mode and therefore be able to get past everything nearby. And this is how it works. And here's another view. You build a structure, you get right past by. So this actually becomes a feature in this video game rather than a bug. Interesting enough. So, and from what I do in cybersecurity research, the more I work on it, the more I realize that there is this gap between theory and practice. We know this famous quote where in theory, there's no difference between theory and practice. In practice, there is. And in cybersecurity, I would like to morph it into, in theory, all security bugs or flaws can be prevented, caught, and eliminated at the same time, ahead of the time. But in practice, they're not. And the reason is because oftentimes when we have our theory designed, it is general enough. It is able to capture a lot of the different things that can possibly go wrong. But the problem is that oftentimes we have a mismatch in assumptions, in the constraints, and the specific domain and environment, right, which often have these different quirky details or differences. And what I do then is a lot of the times I'm trying to bridge the gap between theory and practice by developing the right abstractions. All right, so let's get back to the side channels. So what is a side channel? Here's a real life example in action. This is me on the left. When I was a kid, I used to love playing video games, literally addicted to video games. And obviously my parents wouldn't let me. So they would lock up the game console in a closet and hide the key somewhere. Of course, I was no average kid. I was able to figure out exactly the location of the key. I would go home every day, find the key, get the game console and play video games. Right, so life was fun for some time until one day when my dad came home and he smelled something fishy, right? And he did something that surprised the hell out of me. He touched the TV and felt its temperature. That gave away everything, because even though I was able to hide the game console quickly enough before my dad came home, the fact that the TV was actually hot is a big giveaway. So let's look at what actually happened here. Well, I have this little secret. I was the victim in this particular setup, right? I have some interesting secret, which is whether I'm playing video games. And there's also the attacker, in this case, my dad. And we share some kind of resource, which is the TV. My action of turning on TV and playing video games actually causes the shared resource, the TV, to actually change its property. In this case, the temperature. And the temperature is a property that can be directly observed by the attacker. And hence, my secret is leaked. Okay? And even though this is a real life simple example, it actually is good enough to capture almost every single side channel problem. So we're going to come back to this model later on. So in today's talk, we're going to focus on the TCP and UDP side channels. Specifically, I'll talk about two pieces of TCP side channels and one piece of UDP side channel that actually led to the DNS cache poisoning attack. And make no mistake, side channels in network protocols have been there for a long time. Much of the work earlier, before 2000, are mostly about predictability of, some TCP secrets. But then later in 2007, people started to realize that you can actually find side channels to infer, for example, the TCP sequence number from a completely blind off-path attacker. And then around 2012, we started to look into this problem. And we did a series of work. Here's it's even only a selected set of work in green and red. But I'm only able to cover the red ones today. So, what would be something interesting in TCP? To the attacker? Well, obviously there's one little secret, which is whether a client and server are currently communicating using a TCP connection. That's one piece of secret which we probably are interested in. And there's also the TCP sequence number in both directions. right? Because if you know the sequence number, you can sort of do a lot of things with it. So that is our secret. Who is the attacker? Well, let's go back to the side channel model. Well, the attacker can be, perhaps an eavesdropper or a man in the middle. Well, in those cases, it's probably trivial to observe the fact that there is an ongoing connection, as well as the TCP sequence numbers, right? Because TCP headers are unencrypted by design. But what's more interesting is when the attacker is a blind off-pass attacker anywhere on the internet, right? As long as the attacker is able to probe, the victim. So in this case, what would be the shared resources? Perhaps, the attacker can probe the victim, either the client or the server, and observe, the number of packets that come back or the timing of those responses. But, interestingly, as we show in our work, through some magical shared resources, the attacker is actually able to infer all of the secrets. Meaning, if you give me two arbitrary machines, any two arbitrary IP addresses on the internet, and a blind off-pass attacker sitting anywhere on the internet will be able to infer if these two IP addresses are communicating using a TCP connection. And if so, we're also able to get the sequence number. And imagine the fact that we're able to infer two IP addresses are communicating is already a privacy problem. Let's say if I know your IP address, I can constantly check if you're talking to this server or that server. And if I can know the sequence number, I can even infer how many bytes are exchanged on the connection, and therefore roughly inferring what you're doing on the website. I can also forcefully shut down the connection if I know the sequence number, right? By basically spoofing a TCP reset packet. And finally, if the connection is not encrypted, I can even inject malicious payload, pretending that the packet comes from the client or the server. So this is kind of a big deal. Here's a video demo on the 2012 work that we did, but it applies to the later TCP side channels as well. Now, in this case, we're looking at an Android phone. It was a very old one, where we have a piece of malware running in the background. In this case, a wallpaper app, pretending to be a legitimate app. It doesn't have any special privilege, but if you, let's say, try to open up the browser and go to, let's say, the Facebook website, it actually will start to talk to an off-pass attacker and try to launch this TCP side channel attack. And as you can see here, the web page of the Facebook is actually hijacked, because we're able to infer not only the presence of a TCP connection, but also the sequence numbers of the connection in just a couple of seconds. Now, of course, in the 2012 work, we basically cheated by having a piece of malware running on the client, right? Because if you already have a piece of malware running on the client, you probably can do many other bad things. So in 2016, we looked at the problem again and realized that you don't actually have to have a piece of malware running on the client or the server, right? And this work was published in Using Security 2016. So what we ended up finding is there is this little shared resource, a global rate limit Essentially, it's a single global variable, keeping track of how many packets of certain type has been sent in the past. In this case, this global rate limit is about challenge jacks. And challenge jack is a special type of TCP packet introduced not too long ago. And it was a feature introduced to counter some security problem. And how does it work? Well, basically, if somebody sends some special corner case packets, let's say, to a receiver, the receiver will look at it and say, this packet sounds a little strange. Are you sure you want to send such a packet? That's when the receiver would send back a challenge jack. A concrete example is, let's say, if the client and server already have an ongoing TCP connection, and yet the client decides to send another TCP SYN packet with the same exact port number. The server would be like, okay, hey, we already have an ongoing connection on the same exact port. Are you sure you want to establish another connection? Right? And server would basically send a challenge jack to confirm that it's the real intention. And oftentimes such packets may be injected by an off-pass attacker. That's why the server doesn't want to just trust the packet blindly. And by default, this challenge jack is rate limited globally, meaning it doesn't matter on which connection the challenge jack packet is sent on. It's going to, by default, it's going to be sent at most 100 such packets per second. So what does that mean? It means if the attacker is able to send 100 packets to solicit the challenge jacks, it will be able to solicit 100. And anybody else, if they tried to solicit a challenge jack in the same exact 1 second window, they would fail, right? Because it's a global rate limit. So that's really all we need to know to be able to actually launch the side channel attack. And here's how. All the attacker has to do is to send a spoofed SYN packet, like we talked about, pretending to be the client. And the SYN packet would also contain some source port. In this case, we wanted to guess a specific source port that the client may be using in communicating with the server. If the guess is correct, the server would be like, hey, we already have an ongoing connection on the same exact port. Let me send a challenge jack to confirm that is your real intention. Of course, in this case, the challenge jack is going to be sent to the client, not to the attacker, right? Because the SYN packet was a spoofed packet. But the attacker can indirectly observe that by try and solicit all 100 challenge jacks from the server in that same 1 second window. But in this case, it's able to get only 99 back. Why? Well, there was one other challenge jack that was sent to the client. So 99 is all the attacker will be able to observe. Now, what happens if the source port did not match the real source port used by the client? Or perhaps the client and server doesn't even have a real connection. Well, in that case, the server will not generate a challenge jack to the client. And therefore, if the attacker subsequently tries to send non-spoofed packets to try and solicit 100 challenge jacks, it will be able to get 100 back. Okay, so just by counting, if it's 99 versus 100, the attacker will be able to figure out if the client and server are communicating using a specific port. Okay, here we're assuming that the server port, the destination port, is fixed, because of the well-known services that they're probably supporting. Now, you might be wondering, this is only to guess the port number or the presence of a connection. What about TCP sequence numbers? Well, it actually follows the same exact paradigm. The attacker can actually send some spoof packets to try and guess the correct sequence number. If it's within some rough window, the receive window maintained on the server, then some kind of challenge ACK would be sent. If it's outside of the window, then no challenge ACK will be sent. Right? That's, again, thanks to the feature of challenge ACK introduced in Linux kernel. So we basically would be able to infer the TCP sequence number the same way. And another thing you might be wondering is, are we going to just guess one port number at a time in 1 second? Well, obviously we don't have to do that. We can actually send thousands of packets, guessing different source ports. As long as one of them hits, the server would actually generate a challenge ACK. So therefore, we would then be able to do sort of a binary search on the exact correct port or on the exact correct sequence number. So without going into too many technical details, let me show you the evaluation result. So basically, we participated in a hacking competition and demonstrated this attack. In this case, there is a victim user visiting, let's say, USA Today website. It's a news website. It maintains a long-lived TCP connection to periodically refresh to update the website. And it took us about less than 10 seconds to figure out if there is such a connection, and another 30 seconds to figure out the sequence number in one direction, and then another 10 seconds to get the sequence number in the reverse direction. And once we're able to get all of that information, we're able to inject a fake, a malicious packet, pretending that the packet comes from the USA Today web server. And in this case, we can inject a phishing logging window so that when the user enters the username and password, it's going to actually be sent to the attacker. Okay.
Zhiyun, can I ask a question?
Sure. Go ahead.
About the performance you just showed. Do you need to enumerate all the IP addresses, or do you assume the victim's IP address has already been known by the attacker? That's a good question. So we assume that IPs are given. So if you give me two IP addresses, one is the client's IP, another is the server's IP, we'll be able to launch this attack. Okay, yeah, thank you. All right. Yeah, feel free to interrupt me and ask any questions. So what are the lessons here? Oh, yeah, I get one question as well on the chat. How do you get these IPs? Well, typically we just, if you're interested in launching any kind of targeted attack, let's say if you wanted to target a specific user, well, you can, for example, find ways to establish a connection with the user, let's say on social media, on instant messaging app. Sometimes you'll be able to observe their IP address directly. And on the server side, if you wanted to target a specific kind of website or a specific kind of service, then obviously you should also be able to learn their IP addresses. We also tested the attack against public services like Tor, where a lot of IP addresses that are used to operate Tor are essentially made public. And then you can basically try to disrupt Tor
by shutting down connections, pairwise. So there are many different, kinds of scenarios that, you can, imagine. Okay. I hope that answers the question. All right, so let me move forward. So what are the lessons here? Well, the lesson is we can't really ignore any shared resource, however small it is. Like in this case, it's just a single global variable counting how many packets have been sent so far. And interestingly, we reported this to Linux, and we got a reply from Linus himself in, I think, a day or two. And we were a little worried because Linus is famous for bashing security people and for overhyping security bugs. And interestingly, in this case, he did not do that. And instead, he came up with a patch, which, by the way, was not quite secure. So we had to iterate on it to come up with a more secure one. But Linux was very serious about this. They were able to patch very, very quickly. And in addition to Linux, interestingly, no other operating systems are vulnerable because none of them actually followed RFC 5961, like faithfully, right? But like after we reported this vulnerability, the maintainers of the specification also realized that global rate limit is actually bad, and now they've amended that we should not use global rate limit, right? Because it becomes some kind of shared resource that can enable side channels. So another thing that I want to mention is, you might actually be asking, given that a single global variable can already lead to a side channel, should we try, or can we try to enumerate all possible shared resources in our operating system kernels, or our protocol stack, and try to identify the ones that can lead to side channels? Well, the answer is yes. And we've actually done that in another piece of work in CCS 2019, where basically we tried to model check the Linux kernel implementation, as well as, I think, FreeBSD's TCP implementation. So it's possible. But I wanted to go and talk about another piece of work following the same line of side channel. And yet, in this case, we're not able to easily identify the shared resource, as we showed in the previous work. Right. So as you can probably understand, shared resource is actually the key in understanding side channels, in discovering side channels. And basically, after the 2016 work, we ask ourselves, what are possibly some other shared resources, between the victim and the attacker? Well, we thought very, very hard, and we realized that oftentimes, if we look at what's going to happen in the standard TCP implementation, there are quite some opportunities to allow us to differentiate, if we try to guess something, right, whether the guess is correct or not. We're going to trigger some different behaviors, by design. So let's say if the attacker wants to learn if the client and server are communicating, we can, instead of probing the server, we could also send a spoofed packet to probe the client, right? Pretending that the packet comes from the server. And if there is a connection between the client and server on a guest port, then there's no response from the client. But if we do guess the correct port number, the client will generate a response, according to the spoof packet. But it's just that the response is going to go to the server as opposed to the attacker. Right? So as we can see here, if there is a way for the attacker to infer whether the client has generated a response, then perhaps we can infer whether our guess is correct, right? But the question is, how can the attacker observe the fact that the client has sent a response? Well, it turns out in the wireless networks, you're able to observe this by timing. It's a very interesting, subtle side channel that has been there since the beginning of Wi-Fi, but no one actually realized this until we discovered it. And the key to understanding the wireless network is that it is a half duplex link. What it means is that if let's say both the client and the server are transmitting in the opposite direction, it's actually going to cause interferences, right? Because they share the same frequency bands in uplink and downlink. And therefore, there's basically, you can only transmit in a single direction at a time. And that's the definition of half duplex links. And by taking advantage of a wireless network, an attacker sitting outside of the wireless network, right, anywhere on the internet, can actually take advantage of this to launch a side channel attack, very similar to the one we talked about. And I want to emphasize that the attacker is not actually controlling the wireless router itself. Instead, it's again a completely blind off-path attack. So how are we going to do this? Well, basically, the attacker will send two types of packets. One is the spoofed packets, let's say trying to guess the port number on the client. And the other is some kind of non-spoofed packet to just try and measure timing, or RTT. So let's see how this works. The attacker first sends some probe packets and then followed up by the query packet. Now, if the probe did not guess the port number correctly, what happens? Well, the client doesn't generate any response, right? In which case, the follow-up query packet would actually arrive at the client quickly, without interference, and observe the response also relatively quickly. However, if the probe did match the client port number, guess what? It's going to trigger this ACK packet, which is going to cause the interference with the follow-up query packet. And therefore, the query would have to be delayed, because there's a back-off and retransmission process. And it turns out, if you send enough such probe packets, which is going to trigger enough ACK packets from the client, then it's going to cause enough interference, which is roughly worth 5 milliseconds. And that's significant enough for the attacker to observe whether there is an interference or not. Okay. So this, as you can see, is a timing channel. So we took advantage of this by, again, building a real attack demo. Here, the victim user is browsing, let's say, some malicious website. Perhaps it looks like a legitimate website, where you can play some kind of video games. But if you stay on this website for long enough, what's going to happen is there's going to be a TCP connection initiated in the background, let's say to some kind of banking website. And at the same time, the off-pass attacker would then try to infer, the TCP port number, sequence numbers, and try to send a malicious packet pretending that it comes from the banking website. Okay, and of course it's going to take a little while, which is why we're trying to lure the victim into a website and stay long enough on this website. And here, as you can see, the attack has already succeeded. Of course, it's completely transparent to the user, and he or she is not going to notice anything. But in the background, we've already secretively poisoned the web cache of the banking website. So now, if you try and go to this website, you look at the top of the screen, right? There's actually this username and password login box, which is completely fake, right? When you click login, you are actually sending the username and passwords to the attacker. And this malicious web page is going to be cached for a long time, potentially for months or even years, because we get to control in the fake response that we inject, however long we want the web page to be cached. So you would have to manually clean the browser cache in order to see the clean web page without the fake login window. So yeah, so that's the demo. And we've actually shown that, because this is not a side channel specific to an operating system or browser, we show that it works pretty much for any operating system and browser combination. And the success rate can also be very high, even though it's a timing channel and can be potentially noisy. And of course, if it is noisy, then it's going to take a little longer to finish. And we've actually also demonstrated this in a hacking competition, and was able to get some pretty decent cash award. All right, so what are the lessons here again? Well, it turns out, in addition to the shared resources in the software itself, you can have a global variable. We can also have other kinds of network, shared resources in the network itself, or possibly in the hardware, right? And in this particular case, what we see is that there's this shared resource in the physical and link layer, right, in our Wi-Fi protocol, that can actually have unintended effects on the higher layer in the protocol stack, specifically TCP. So we've actually reported this to the IEEE 802.11 working group. And surprisingly, what they told us is that there's no real solution to solve this problem, because all generations of Wi-Fi are by design half duplex, right? And therefore there's nothing they can do. So if you want to play with this, we've actually open sourced the demo source code, and you can actually still make it work in today's Wi-Fi networks. All right. I guess I want to quickly finish the last piece of work, which is the side channel on UDP. It is very much similar to the using security 16 work, but the application is a lot more interesting, or I guess you can say that it's more serious. So we've talked about TCP side channel, but what about UDP? The first thing we're going to ask again is, what are the secrets in a UDP session? Well, the most obvious answer is the port numbers, or the fact that the client and server are communicating in UDP. So why is that important? Well, it's important because some application layer protocols, such as DNS, relies on the fact that this port number, especially the source port number of a DNS request, is randomized. Right? It relies on the fact that it relies on the entropy provided by the random source port number, right, for security purposes. And for those of you who are not familiar with DNS, here's roughly how it works. Let's say if you're a client, you wanted to visit, let's say, facebook.com. Well, you wanted to first know the IP address of the domain name, and therefore your browser would issue a DNS query to your local DNS resolver, which may be 8888 or some other resolver provided by your ISP, and the DNS resolver then would try to contact the authoritative name server provided by, let's say, Facebook, and it's going to send this DNS request to Facebook's name server. And then in response, the name server would tell you the actual IP address, which would then be cached by the DNS resolver. So what prevents an attacker, let's say a blind off-pass attacker, from pretending to be the legitimate name server and inject a fake response? Well, there are two secrets if we zoom in to the DNS request. There's this source port, which is supposed to be randomly generated by the DNS resolver, and it's 16-bit long. And there's also this transaction ID at the DNS layer, which is also 16-bit long, randomly generated. So if an attacker wants to brute force, it's going to cause basically 2 to the power of 32 guesses, right, to have a match in both the source port and the transaction ID. And that's probably not feasible. However, if an attacker can guess the source port independently, then it's going to basically be a lot easier to brute force, right? In the sense that we only need to guess the two 16-bit secrets sequentially, as opposed to all at once. Right? And if the attacker is indeed able to do that, then we will be able to inject a fake DNS record, a malicious one, and have it cached at the DNS resolver for a long time. All right, so how would this work? Well, it's pretty similar. You would have the secret about the port numbers, and then you have an off-pass attacker who's able to, let's say, probe the victim and again observe some kind of response. Okay. And believe it or not, it's the shared resource in this case is again a global read limit, just like the TCP case. It's just that the global read limit here is more specific to UDP. And in this case, there's this ICMP global read limit that constrains how many outgoing ICMP port unreachable messages can be sent per second, right? And it's a global rate limit governing all destinations. This doesn't mean which IP address you're sending the ICMP to. By default, you can only send 1,000 such ICMP messages per second. This is to save the network resources, because you don't want to send too many ICMP packets in response to some kind of probes. It's considered a waste of resources by the operating system. So what can we do? Well, we can probe, let's say, our DNS resolver and try to solicit 1,000 ICMP port unreachable messages. It's going to basically drain the rate limit completely, right? So to the point where the DNS resolver is unable to send any other ICMP message, to anybody else in the same 1 second window. So yeah, so how do we exploit it? Well, it's gonna sound very similar to TCP. We send a spoofed UDP packet, pretending that the packet comes from the name server. Sorry, there's a typo here. We're not actually pretending to be the client. We're pretending to be the name server. And we're basically guessing some kind of port. And if the guess is wrong, then by design, our DNS resolver will basically generate this ICMP port unreachable message, right? Because we didn't hit a port that is currently being used. Of course, this message is going to be sent to the name server, so the attacker cannot directly observe it. But it can indirectly observe it by try to send 1,000 UDP packets, non-spoofed UDP packets. And this time it's able to observe only 999 back. Well, why? Because there's one other ICMP message that was sent earlier. Okay. So what if the attacker actually made the correct guess of the port number? Well, in that case, there's no ICMP that's going to be triggered by the DNS resolver, on the DNS resolver. And subsequently, the attacker should be able to observe 1,000 ICMP messages all to himself, right? So again, by counting, if it's 999 versus 1,000, the attacker will be able to infer if the port number, the guessed port number is correct, right? And therefore, we're able to launch the DNS cache poisoning attack, subsequently. So it turns out this is affecting a lot of DNS resolvers, that have caches on the internet. So there are 34% of open resolvers on the internet, public DNS resolvers on the internet that are vulnerable. And if we look at the popular ones, 12 out of 14 are basically vulnerable, including all of the famous ones, such as Google's DNS, Cloudflare, and so on. So one other thing that you might be wondering is, the attacker might have a very small window of opportunity to infer the port number. And yes, that is correct. However, we're actually able to cause the name server to become unresponsive by flooding it or sending some DNS requests ahead of time to trigger some kind of rate limit on the name server itself, so that it won't be able to answer the legitimate DNS resolver's request. Okay, and that way we can extend the attack. We can extend the attack window to a couple of seconds. So we actually tested our attack against a production DNS resolver in Tsinghua University, and it serves 70 million queries per day. And we're actually able to successfully poison the cache. And we also tried a popular commercial public DNS service with authorization, obviously. And we also succeeded, under realistic network conditions. So the network doesn't have to be perfect. Right? There can be packet losses or jitters and so on. So we've tried this and succeeded 5 times out of 5 times out of 5 against the Tsinghua DNS cache. We also succeeded once in just under a couple of minutes against the commercial DNS. So I wanted to wrap up. I know we're running short on time. By concluding that, if you haven't heard of network side channels, now you probably will realize that they are actually real. They're weaponizable. There are a diverse set of root causes, be it from shared resources in the software or in the network, by design. And it's actually interesting to look into these different scenarios and come up with different exploitation techniques. And perhaps this is a unique property of side channels. Oftentimes it's hard to fix if it's something by design, right? Unlike some of these other security vulnerabilities. So I guess I won't talk about the future work. I'll basically stop here and take any questions.
Thank you very much. Right, it's really a very excellent research and also a very nice talk. So I have 2 questions. The first question is about currently a lot of websites or many services, they are actually using like TLS. What is the implication of using TLS with regard to this type of attacks?
Right. So that's a good question. Yeah. Of course, we showed that the attack on web pages, but it's not just the websites that run over TCP. There in fact many different applications that run on top of TCP. I mentioned Tor, where they're encrypted as well, but we can still shut it down by forcefully injecting like a reset packet, right? Once we know the correct TCP sequence number. We can also, attack email connections, FTP connections, any other applications that run on top of TCP, basically.
Right. Right. So that means even we have TLS or encrypted communication channels, the attacks, they are still possible and they can still cause some damage to the victims. Right,
right. At the very minimum, they're able to infer if there is such a connection, which is a sort of a privacy leakage, if you will. Okay. And also we can shut it down forcefully. Okay, yeah, that's very interesting actually. So my second question is about the research methodology. So it's very interesting to see actually you start the research by finding out what are the shared resources and then develop attacks around this shared resource. So how do you find those shared resources in the first place? By reading the specifications or by analyzing the code or by some other method? Yeah. So that's also a great question. At the very beginning, I stumbled on such a shared resource back when I was a PhD student. So that was 2012 when I first discovered, some shared counters, global TCP counters, statistics on like how many packets have been sent out, how many packets have been received, how many packets received are, with bad checksums, and so on. Right. So that was my first observation that, this is a global, resource and it's shared. And then later on, once I know this, I started looking into other kinds of shared resources, other kinds of like variables in the source code. In fact, in the using security 16 work, what I did was I basically manually eyeballed the Linux source code when I was on the airplane thinking about my first NSF proposal. I needed some preliminary results, right? That's how I discovered this.
Oh, right, that's interesting. So let's see, are there other questions from other people?
Hi, just wondering, I mean, when you mentioned this, the global rate, what's the solution there that will be able to sort of provide us with the global rate was there for a reason, right?
Right. Yeah. So that's, so I forgot to mention the details, but basically you wanted to either provide an isolated, like per connection rate limit, or maybe you want to randomize. If you really want to have a global rate limit, you want to randomize it. And that's exactly what Linux did, by the way. They did both.
Right. So, and this random rate limit doesn't need to be known by the two parties. That doesn't need to be agreed on by the two parties, right?
Because this is sort of the rate limit is only to sort of to limit the resource usage on the receiver side. So whoever is receiving a lot of probes and generating a lot of responses, they want to limit the number of responses to constrain the resource consumption. So it doesn't really need to be negotiated with the other side.
Sure. Great. Thank you.
Okay. David.
Hi, thank you for the presentation. It was very interesting. I was wondering about what you said of the problem with Wi-Fi, that it's not possible to fix it because it seems like something in the hardware or something like that. I'm not really sure about this. If you can explain a little more about this. And if there is the same problem in Bluetooth, for example, or other protocols, have you tried those?
That's an interesting thought. Yeah, so any protocol that is half duplex potentially would have this side channel, right? Because whenever you have half duplex links, you're not allowed to transmit in both directions, uplink and downlink, and therefore, whenever you do transmit in both directions at the same time, there's going to be interference, and there's going to be a backoff and then retransmission. So that causes a timing channel, meaning if you do have simultaneous transmissions, then there's going to be a delay in transmitting your packet eventually. Right. So at the lowest layer, in the wireless layer, physical layer, there's going to be retransmission. That's why it's going to take longer to reach the destination. I'm not sure if that's clear.
Yes, but so a 5G, for example, connection that I think is not half duplex, then would it be more secure than that? For this kind of attacks, wouldn't be possible?
Yeah. I think we haven't looked into 5G specifically, but if it's not half duplex, if it's full duplex, then yeah, it should be secure. It should be free from this type of side channel. That's right.
Thank you.
Sure.